Here we're going to do a two-proportion confidence interval and hypothesis test. First thing we want to realize is that the formulas for the standard deviation of the sample proportions is a little bit different in the cases. So in the confidence interval, you got this formula for the standard deviation of the sample proportions, which uses the p-hat sample proportions, whereas in the hypothesis test, we pool together the number of successes in the two samples divided by the number sample size in the denominator to get a pooled proportion that we then stick inside here. Instead of the p-hat, we do the pooled, and we do the q pooled, which is 1 minus p pooled, and that's the same. So this is the same as this. We're just dividing by different ends. So that's the something to take notice of. So here's our example for the confidence interval for the difference of two proportions. In a study of treatments for very painful cluster headaches, 153 patients were treated with oxygen and 158 other patients were given a placebo. Among the 153 patients in the oxygen group, 107 were free from headaches 15 minutes after treatment. Among the 158 patients given the placebo, just 34 were free from headaches 15 minutes after treatment. So I'm making up the question here. Find a 95% confidence interval for the difference between the population proportion of patients headache-free in 15 minutes when treated with oxygen and that of patients given a placebo. So if P1 is the oxygen group and P2 is placebo, then we're after this difference here for the true difference in the population proportions. So we look at our formula that we've got to have, and we realize we need the p-hats in there. We need it here and here, and so we calculate those. 107 out of 153, 34 over 158. We get these numbers here. The n sizes are here that was given. Now we're going to go for the z critical to put here to get the error for the confidence interval. And what you really should do at this point in the course is you should have made a chart of all the popular one-tail and two-tail z-critical values for a given alpha levels of significance for hypothesis tests and for confidence interval levels, because you'll see the same ones pop up over and over again. But anyway, just in case we need to drive it on the spot, we're going to use the inverse norm function of the calculator, which we've gone over in other videos. And if you put in here, this is the area below your z, and so that's going to give you this tail here, which gives you a negative 1.96, and then you realize by symmetry that the one over here is 1.96. It's a two-tail, which all confidence intervals are, so it's the 0.05 was split into the in two. So anyway, you get 196. You could also get it by doing the area below this z critical, which is 1 minus 0.025, and you're going to get 1.96. Okay, so anyway, you get your z critical. Then your error, therefore, is going to be z critical times this version of the standard deviation of the sample proportions that we're supposed to use for a confidence interval. You stick your p-hat in there, and the q, p-hat number 2, q2 over the ends, square root. This is how it looks in the calculator if you do it that way. Error is 0.097. So the point estimate is this difference between p-hat 1 and p-hat 2, which I should have put a minus right here, so we're going to correct that right now as soon as I do this. So I made that correction that it's a minus, of course. And so here's how it looks in the TI. and you get 0.484 point estimate. So then your normal template for any kind of confidence interval is to do the point estimate minus the error up to point estimate plus the error. So we just put in the numbers that we had, and we get this confidence interval here. So then you don't just say what, you just don't write this interval mathematically, you do a statement. And this statement you get right from the original problem. You just copy it right out of it. The difference between the population proportion of patients headache-free in 15 minutes when treated with oxygen and that of patients given a placebo is between 0.387 and 0.587. Now you should also realize at this point that 0 is not in that interval. And the interval covers just positive numbers also. So right now we're thinking that the P1, that's the treatment with the oxygen, minus the proportion with the placebo is greater than 0, because it's positive numbers and 0 is not an interval, so it's greater than 0. So that means that the proportion of the treatment is going to be greater than the proportion of the placebo by just adding this over to the other side. That is, we think already that the treatment raises the proportion of headache-free patients. That is, it works. But now let's do an official hypothesis test to see. Okay, so here's your hypothesis test. The same exact problem, except this time I'm using the statement that was there. So it's the same patients, the same number of headache-free people in 15 minutes, and in the placebo group. But this time it says use a 0.05 significance level test to test the claim that the oxygen treatment is effective. Okay. So P1 is the true proportion of headache-free patients when treated with oxygen. P2, same thing except for receiving the placebo. So in this story, effective is what we're looking for, and that means that the oxygen proportion is greater than the placebo. That's what we want to show. So we're committed to a one-tail test. HO has equals always. That also means that the difference is hypothesized to be 0. The alternate is that P1, the treatment with the oxygen, is greater than the placebo proportion, which also means that the difference is alternately being greater than 0. So we have our formula here, and we do the P-pooled. We follow the directions of the P-pooled, and we execute it here, get the P-pooled proportion, and then we get the difference. We need this difference of P-hats, so we do that, and you get the 0.4842. So then you're looking for your Z value for your difference in sample proportions, and that's going to be the difference in the sample proportions minus the hypothesized difference of the population proportions, which is 0, which is kind of nice because it's hypothesized to be 0 right here. So then you go and you divide by your standard deviation of the sample proportions, but this time you're using the pooled P, that's the P bar, pooled P and Q, and you stick your numbers in there. This is the way it looks on the TI, and it comes out an outrageous Z. You already know by this time in the course that when you see a Z of 8, that's way extremely far out into the right tail. So you already know it's going to be a reject. So alpha is 0.05, one tail to the right. There's your rejection region here. And the Z critical happens to be 1.645, that you could obtain that. And you see that your 8.58 is way out beyond that. So it's going to be a reject. But anyway, we can find the actual p-value. It's a one tail, so it's the whole area out there. It is 8.58. That's our Z, all the way up to 10, which is virtually almost no areas out there. 0, 1 for the mean and standard deviation of the Z line. And that turned out to be 4.8 times 10 to the negative 18. Your calculator says E instead of the 10. It means 10 to the negative 18. So it's virtually zero, very small. So almost no chance of being out that far. So we're going to really reject HO because the p-value is less than the alpha significance level, way less. There is significant evidence to support the claim that the proportion of 15-minute headache-free patients using the oxygen treatment is higher than that of patients given a placebo. And that's at the alpha 0.05 level. P-value is practically zero. In other words, the oxygen treatment works.